Hello everyone. Gauss law applied to different charge distributions we discussed previously. Now another application of Gauss law, that is Gauss law applied to differential volume element. We will give the Gauss law applied to differential volume element, that is Maxwell's first equation will be obtained from this theory. Application of Gauss law where the field is non-uniform. Suppose if the charge is distributed uniformly, we can apply Gauss law easily, previously what we discussed. But if the field is non-uniform, we have to consider a differential volume element. That is Gauss law applied to differential volume element. Point form of Gauss law also can be obtained from this derivation. And another name for this is divergence equation. Gauss law applied to differential volume element, or point form of Gauss law, or divergence equation or divergence theorem, Maxwell's divergence equation for electric fields. All are same. You can see the video until the end. You can understand what is Maxwell's divergence equations, Maxwell's laws, what is divergence theorem, or Maxwell's first equation, application of Gauss law where the field is non-uniform, the point form of Gauss law. All this will be obtained from this derivation. Up to now, we discussed the various cases in which there exists a symmetry in d bar. In d bar, there exists a symmetry and it is normal to the surface and constant everywhere on the surface. We consider sphere, we consider cylindrical, one cylinder, or we consider a different a ds on the cylinder, that is constant over the surface. But there exists a symmetry and a Gaussian surface cannot be chosen. If the field is non-uniform, the symmetry and Gaussian surface cannot be chosen, such that the normal component of d bar cannot be chosen for non-uniform field. Gauss law cannot be applied directly. Non-uniform field non-uniform గా ఉన్నప్పుడు Gauss law we can't apply. అప్పుడు మనం పోవాల్సింది differential volume element. We have to consider the differential volume element. The Gauss law applied to differential volume element, Maxwell's first equation we can derive from Gauss law applied to differential volume element. For uniform fields, we have to consider a differential closed Gaussian surface. Assume that a differential closed Gaussian surface is in xyz coordinate, that is Cartesian coordinates. It is x-axis, y-axis and z-axis. And z-axis it is. For the closed surface, a small surface, we are assuming a differential volume element, d bar is almost constant. Consider a differential volume element. Volume means here three coordinates x, y, z. A differential volume element having delta x, delta y, delta z. Like this we have to draw a differential volume element. We have to draw the differential volume element having height is delta z and width is delta x and breadth is delta y. Assume that it is a differential volume element. This is in y-axis direction. It may be considered as delta y. It is very important to know Maxwell's first equation also. Hence, observe carefully or listen carefully, and finally we will get divergence theorem, divergence equation. This is delta x and height of the differential volume element, it is delta z, and width is delta x. It is delta x. It is delta x, it is delta y, it is delta z. It is the differential volume element. Here we are applying the Gauss law. A point P is located in differential volume element. A point P, assume that. Consider a Cartesian coordinate system and a point P in it such that the electric flux density at point P is given by Assume that point P electric flux density is given by d bar equal to d naught. D bar equal to d naught. Assume that. In Cartesian coordinate system, the electric flux density is given by d bar can be written as dx ax plus dy ay plus dy ay plus dz az. Now we consider the closed Gaussian differential volume. Consider the closed Gaussian differential surface in the form of rectangular box, which is a differential volume element, it is known as. The sides of the elements are delta x, delta y and delta z. This is the delta y, this is the delta x and delta z. Three sides are. The position of this element is in such that the point P is at the center of the element. The point P is at the center of the element and treated to be origin. Assume that point P is center of the element. Assume that it is a point P here. Assume that point P center of the element. Hence d bar at P can be denoted as d naught. We can write d naught. It is d bar can be written as at origin it is a d naught. In this diagram we can see it is a differential volume element. The electric flux density at point P can be resolved into d bar equal to dx ax. In Cartesian coordinate systems, we can resolve any vector along x, y, z axis, dx ax plus dy ay plus dz az. Assume that at origin the electric flux density at this position is d naught. D naught is this. Let d bar equal to d naught. Assume that. Let d bar equal to d naught, that equal to dx naught, because it's already we written as x dx ax in all components. We are writing dx naught ax plus dy naught ay plus dz naught az. We can write like this at the point P, because point P is located at origin. The components of dx naught, dy naught and dz naught vary with the distance in the respective directions. In the respective directions, according to dx naught means from the origin in x direction, from the origin in y direction, from the z direction it is dy naught, dz naught. Now we are applying the Gauss law for differential volume element. Once again I am saying that if the surface is symmetrical, like cylindrical coordinate system or spherical coordinate system, we can apply. If the surface is non-uniform, if the field is non-uniform, if we can't apply the Gauss law directly, we have to consider a differential volume element. The dx naught is in this direction. The dx naught is, this is the dx naught, the electric flux density in x direction from the origin. Dy naught, this is dy naught. We can write what is dy naught. It is dy naught and it is minus dy naught. Assume that electric flux density in negative direction. Similarly in z direction dz naught, it is dz naught. Negative of that axis is minus dz naught. Electric flux density in negative of z direction. Now we are applying Gauss law for this. According to Gauss law, what is Gauss law? The total charge Q equal to, according to Gauss law, total charge Q, that is according to Gauss law, it is according to Gauss law. According to Gauss law, the total charge Q equal to surface integral d dot ds. Surface integral d dot ds. The total surface integral to be evaluated for 6 surfaces. Already we saw that in the diagram. The 6 surfaces we have to observe. You can observe the 6 surfaces minus dy naught, plus dy naught, dz naught, dx naught. Negative of direction of that one is dx naught. It is the negative direction dx naught. 6 surfaces we assumed. The total surface integral to be evaluated over 6 surfaces, that is front, back, left side, right side, top and bottom. Over the 6 surfaces we have to apply front, top, bottom, right side, left side. For all surfaces we have to apply the Gauss law. Hence we can see, according to Gauss law, surface integral d dot ds equal to q. Make it as equation number 1. The total surface integral to be evaluated, that is LHS, we can apply, right? LHS or RHS. It is RHS. Assume that from this RHS, surface integral d dot ds equal to, we are applying the Gauss law for entire integration is carried out for front plus back plus integral left side plus integral right side plus top plus bottom d dot ds. The integration is carried out over all the surfaces, that is d dot ds, the multiplication of. Make it as equation number 2. This is the equation number 2. The integration is carried out over 6 surfaces, that is front, back, ls, left side and right side, top and bottom. Consider the front surface of the differential volume element. For the front surface, we are applying first one. Consider the front surfaces. Let us see that. Now consider the front surface. Consider the front surface. Consider the front surface of a differential volume element through d bar is varying with a distance. For small distance surface like front surface, it cannot be assumed constant. Now we are applying front. It is the front d dot ds equal to front d dot ds equal to what we can write. D bar can be written as, we have to apply for front. D bar in front side is df. Assume that df is the dxf. In d bar direction is d front or dxf. We can assume that d bar can be written as d front, and ds can be written as, ds bar can be written as, for a Cartesian coordinate system, ds is, what is the formula for ds is delta y delta z ax direction. It is in ax direction, or dx also it is in x-axis direction, it is different. For that, ds is remaining two axes, delta y delta z product will be considered. We can write dx front instead of like that. We can write this for front d dot ds equal to, for front d dot ds equal to, now we can substitute in place of d bar, this we can substitute, and ds in place of that we have to substitute this. How can you obtain ds bar? For ds bar in x-axis direction, we have to consider another two coordinates, delta y and delta z, ax. The direction is ax. That is the formula already we obtained in Cartesian coordinate system. Now we are substituting in place of d bar and ds bar, these two, that equal to front surface integral front d dot ds can be written as dx front plus dot ds is delta y delta z ax. We can write like this. But different equal to, what is different? Dx front ax in x direction it is. Hence we have to substitute in x direction dx front. Dx front is in x-axis direction. Hence unit vector is ax dot delta y delta z ax. What is the x dot ax? Ax dot ax is 1. Since ax dot ax equal to 1, we can write, since ax dot ax equal to 1, this dot product becomes 1. Then finally we will obtain surface integral front d dot ds equal to d front delta y delta z. We can obtain that. We have to write. Therefore we can write front as d dot ds equal to d front delta y delta z. As ax dot ax is equal to 1, we obtained already. Assume that it is a, make it as equation number 3. Assume. But dx front is changing in x direction. You can see the diagram. But dx front, if you assume that dx naught, it is dx front is dx naught, in x direction it is. Dx front is changing in x direction. At point P it is dx naught, while the front surface will be changed and is given by dx front equal to dx naught plus rate of change of dx with x into distance of surface from the point P. That is, we have to consider dx front can be written as, now dx front can be written as dx front can be written as dx naught. Initially at origin electric flux density is dx naught plus rate of change of dx with x-axis, rate of change of dx with x-axis, that is x-axis, into distance of surface from point P. That is another formula. Distance of surface from point P. Distance of surface from point P we have to consider. That we can write as dx front equal to dx naught plus rate of change of dx with x-axis, that is the partial differentiation, dou dx by dou x in x-axis direction into, that is multiplication, distance of surface from point P, that is delta x by 2. It is half of the distance. It is the corner, it is the origin. At origin the point P is delta x by 2 is the distance. This is the delta x dx front electric flux density in front direction is dx naught plus dou dx by dou x into rate of change of dx with x, that is known as dou dx by dou x into distance of surface point P, that is delta x by 2. These are we have to consider. The point P is center, so that the distance of surface in x direction from point P is delta x by 2. Similarly in y direction is delta y by 2. The rate of change is expressed as potential derivative, that is partial derivative, as dx varies with y and z coordinates also. Therefore we can write surface integral front d dot ds equal to dx naught. We can write surface integral d dot ds for front can be written as dx naught plus dou dx by dou x into delta x by 2 and ds is delta y by delta z. Therefore we can write like this. Therefore front d dot ds, therefore we can write front d dot ds, integral front side d dot ds equal to dx naught delta x by 2 dou dx by dou x into what is ds? ds can be written as delta y delta z. Consider the integral over the back surface. Similarly we have to consider for back surface. How to obtain back surface? Integration, therefore for back surface, that is minus ax direction, it is for back surface. For back surface, if you consider the back integral d dot ds equal to approximately or equal to d bar back d back dot ds. Similarly we have to apply where d back is dx back and ax direction, it is ds is delta y delta z but a minus ax direction. Now we can substitute. Similarly front ఎలా substitute చేసాము, ఇప్పుడు back side అలాగా substitute చేస్తే we can write d back as dx back dot ds is delta y delta z but direction is minus az direction we have to consider. Similarly it is also not az, it is ax. Delta y delta z into minus ax direction, it is the area is minus ax and it is dx back also, it is also in x direction, we can write ax, the x direction dx back also. Therefore we can write the flux is entering from back side and leaving from the front side in position x direction, hence ax is used to positive for back also, while the surface is considered from the point to negative x direction, hence minus ax is used for expressing the ds, that is ax dot ax equal to 1 again. Therefore we can obtain back side is dx back delta y delta z, that equal to dx back flux direction in back side ax dot ax equal to 1. Already it is a negative and positive, but we have to consider ax dot ax is 1, ax dot minus ax also 1, dx back delta y delta z we can obtain, because ax becomes ax dot ax is 1, since ax dot ax equal to 1, that we obtained. Front side how we are applied, same procedure we applied for back side also. Now dx back is changing with x direction, at point P is dx naught. Similarly we have to assume what is the dx front, dx naught plus rate of change of dx with respect to x into distance of surface from point P. The same procedure we have to apply for this also, you can see now. Now dx back is therefore dx back equal to dx naught minus rate of change of dx with x, it is a back side, hence we represent it as rate of change of dx with x, that is dou x by dou dx by dou x into distance of surface from point P. Same formula we have to write here also, delta x by 2 we have to write. The negative sign is used as the surface is in negative direction of x from point P, because the negative direction it is, hence we use negative sign. The negative sign why we are using, because it's a x direction but it is negative of x direction. Substituting this equation this equation surface and back side d dot ds, surface substituting here, d dot ds equal to minus dx naught minus delta x by 2 dou dx by dou x into ds can be written as delta y into delta z, we can write. Assume that the equation is 4. This is the equation 4, and previously front we obtained, you can see that front side d front is equation 3. Assume that it is d front, we can is dou dx by dou x delta x by 2. It is equation number 3. Already we assumed 3. Again it assume that it is a 3a or 3. Now we are surfacing. Now back surface and front surfaces, two we are combining the equations 3a, and another equation is backside equation. The backside equation is 4. Combining the equations, that is already we saw that front side is front side plus back side we assumed. Because it is a front and back, we are combining the two equations here. What will happen? 2 into delta x by 2, because dou dx by dou x delta y by z, delta y delta z. If you substitute this equation 3 and 4 here, we can write as combine the equations 3 and 4. From equations 3 and 4, integral front plus integral back equal to, if you substitute the two equations, dx naught minus dx naught get cancelled. That is front side is dx naught plus delta x by 2 dou dx by dou x into delta y delta z. That is the front side, the front equation, plus we have to add back side. The back side is minus dx naught plus, if you made common, minus dx naught plus delta x by 2 dou dx by dou x into delta x by 2. Already we written the delta x by 2, delta x by 2 dou dx by dou x into delta y delta z. Combining these two equations, dx naught get cancelled. After cancelling this dx naught and minus dx naught, we are obtaining the 2 into delta x by 2, that equal to, we can write as 2 into delta x by 2 dou dx by dou x into delta y delta z. We can write like this. That is front and back equation is 2 into delta x by 2 get cancelled. Now that equation is, the equation for that delta front and back side is, we can write as dou dx by dou x into delta x delta y delta y delta z, because already delta y delta z is there. Here 2 get cancelled, delta x is obtained, delta x delta y delta z. That is, similarly we can write left and right side also. How we applied previously for front and back, similarly we have to consider for right and left also. Let us see that. Similarly, we can write for left, integral left, Gauss Law applied for left side plus right side. We can write as for left side and right side. Left and right is in y-axis direction. Left and right, or that is left and right is, this is the y-axis, negative of y-axis, it is positive of y-axis. Therefore integral left plus right can be written as dou dy dou y-axis direction. The field is electric flux density is y-axis direction. Similarly we obtain delta x dou dy by dou y delta x delta y delta z. We can obtain, make it as equation number 5. Similarly if you apply the top and bottom also, for top and bottom, how can you write? For top and bottom you can write the equation similarly for front and back ela rasaru alage for top and bottom plus bottom. We have to consider both because top and bottom, front and back. If you consider like that, you will get cancel the each terms negative and positive directions. After that it is bottom. If you apply the bottom side, front and bottom, top and bottom is in z direction, that is dou dz by dou z delta x delta y delta z. Make it as equation number 6. The equation number 6. Therefore we are obtaining the, substituting the 5 6 4 3 2 1 all the equations in Gauss law. All the fifth equation, sixth equation and fourth equation, third equation, front back plus top and bottom, left and right. If you substitute all the equations, what you will obtain? The surface. Therefore surface integral d dot ds, surface integral d dot ds equal to, if you substitute all the equations, you can write dou x by, we can write by substitute all the equations 3 4 5 6, dou dx by dou x plus delta x delta y delta z, all the common, we are making the common, plus dou dy by dou y plus dou dz by dou z into the common term is delta x and delta y, delta z is common, hence we can write delta x delta y delta z. But delta x delta y delta z is differential volume. The differential volume, differential surface is dx dy and differential volume is delta v. We can substitute in place of this delta v, we can directly substitute in place of this is delta v, we can substitute, that is delta v, delta x delta y delta z is differential volume. Hence the total charge enclosed in differential volume delta v is given by the q equal to surface integral d dot ds equal to dou dx by dou x plus dou dy by dou y plus dou dz by dou z into delta v. This is the total charge enclosed in volume delta v is given by this formula. Therefore we can write delta v as the total charge enclosed in volume, differential volume is, therefore the total charge enclosed in differential volume d dot ds equal to q. If we substitute all this, we can write q equal to surface integral d dot ds. After substituting all this, that is in differential volume, what is the total charge enclosed? In a differential volume, we consider one small differential volume element. In this, what is the total charge is? First we applied front, back, after that left and right, top and bottom. That is q equal to charge enclosed in differential volume element dv. It is delta x, delta y, delta z. Product is delta v. Charge enclosed in differential volume delta v is q equal to, this formula we have to remember. It is very important. Dou dx by dou x plus dou dy by dou y plus dou dz by dou z into delta x, delta y, delta z. That can be written as delta v. It is a differential volume. This results lead to concept of divergence. This result, ఈ ఈక్వేషన్ నుంచి మనం కాన్సెప్ట్ ఆఫ్ డైవర్జెన్స్ వీఆర్ obtaining. What is divergence? That is concept we are going now. Okay, let us see again, repeat that from the starting onwards for differential volume. If you understand this, then you can easily understand divergence theorem and divergence, Maxwell's first law. Okay, let us see again, repeat. In the previous classes we discussed about for spherical and cylindrical coordinate system, if the Gaussian surface it is a uniform surface, we have to apply directly the Gauss law. For non-uniform fields, for application of Gauss law for non-uniform fields, we have to consider differential volume element. Differential volume element like delta x, delta y, delta z, or the three sides of a cube, volume cube, or differential volume element. The d bar in x direction can be written as dxax plus dyay plus dzaz. Now suppose assume that a point P is located at origin. The point P is located at origin. At this point P, what is the electric flux direction is all coordinates is dxax, dyay, dzaz. We can write it is at origin, we can write d bar as d naught. If at origin it is dx naught ax plus dy ay plus dx dz naught az, we can write like that. From now we are applying the Gauss law. We can see that Gauss law. According to Gauss law, the total charge enclosed in any surface or any volume is q equal to surface integral d dot ds. That is the Gauss law. Make it as equation number 1. Now we are applying the Gauss law for entire volume element, that is differential volume element. Surface integral d dot ds equal to d dot ds into all the integration, all sides, front, back, and left side, right side, top and bottom. We are considering all the surfaces. First we go for front back at a time, because in x direction it is front, negative of x direction is back. Now we can see that from front and back we are changing the rate of change of electric flux density dx naught plus rate of change of electric flux density into distance of point P from x-axis direction, that is point P is delta x by 2, at half of the distance it is. Finally we obtain dou dx by dou x, delta y, delta z after substituting all this. Now after that we go for similarly left and right side. We can apply left and right is comes under y-axis direction. Similarly, if you apply the Gauss law, dou dy by dou y, dou delta x, delta y, delta z, you can obtain. If you are not understand this, again we will go for that. Again see that. Coming to right side, d dot ds equal to, in right side, that is in y-axis direction, that is delta y, or it is dy direction. It is, or assume the differential volume element, this is dy direction, dy right side it is, we can write dy right side into ds right side. Ds is in right side is y direction, ds can be written as y direction. We accept that dx and dz will come. ds bar in y direction is dx dz. ఇక్కడ y డైరెక్షన్లో అయితే రిమైనింగ్ 2 కోఆర్డినేట్స్ వస్తాయి, dx dz, that is ds. Similarly we can write d initial point at dy naught plus change of electric flux density in y direction, partial differentiation dou dx plus into point P at a distance is delta y by 2. Similarly, previously we assumed that delta x by 2. Similarly, if you consider right side, it will be negative. This will be cancelled. Finally, we can obtain in y direction is dou dy by dou y, delta x, delta y, delta z. Why we obtain this? Already 2 will come. a 2 will come 2 into delta x by 2 delta y by 2 already previously delta x by 2 వచ్చింది ఇక్కడ 2 into delta y by 2 వస్తుంది అప్పుడు 2 గెట్ క్యాన్సిల్ అయిపోయి delta x delta y delta z that is left. Similarly right side, if you apply the similarly left and right, you can obtain delta x dou dy by dou y delta x delta y delta z. I understand this, I think. After substituting all this front back left and right all this, you can substitute dou dx by dou x plus dou dy by dou y plus dou dz by dou z into delta x delta y delta z we are obtaining. Delta x delta y delta z is nothing but differential volume delta v. Hence we can write the total charge enclosed in differential volume delta v is given by q equal to dou dx by dou x. This formula, it is very important. This formula used to concept of divergence. Okay, the concept of divergence we'll discuss